Hey guys, so we're going to start looking at some utility-based decisions inside our architecture. So if we look at our sort of guard controller, the sort of AI guard that we've got so far, this is pretty much what we've got. So we've got the pawn sensing, checking to see if the enemy's got a tag. I've done a couple of prints here just to make sure I know what's going on, and then setting that value as the kind of target for us to attack inside the blackboard. So what we want is something that can detect multiple enemies and prioritize which one they're going to attack. So I wanted to talk about this idea of utility as a sort of part of a behavior tree, or as just part of decision making in general. So let's have a quick kind of look at where we're going to go with this. So I've been breaking out these things into small blocks of code in the blueprints, and what I'm going to do now is instead of just setting it in the blackboard, what I'm going to do is I'm going to, when I see a pawn, check it's got the tag, and instead add it to a threats list, right? So there's going to be a bunch of threats in a bunch of data structures, and we'll talk about those later. And then every tick I'm going to evaluate those threats, so go over that array and look at which is the sort of which is the highest threat, and we're going to do that only every threat evaluation frequency. So basically, like, so at a set interval we're going to evaluate the enemies, and then we're going to do the evaluation here, find the maximum value and set it in our behavior tree, and then finally set that behavior tree object as we did before, so inside the blackboard. But before we get to that, I wanted to sort of bring up something in terms of the actual behavior tree itself. So let's just load up the other map. Level item. So we've got this guard behavior tree, which just so happens to be on the wrong monitor. There you go. And one thing you should kind of notice here is that the conditions, the things that allow our behavior tree subtrees to run, are all essentially on-off, right? They're all true or false statements. And also the structure of the behavior tree is kind of important in that the priority of running the behavior tree nodes runs left to right. So higher priority here, lowest priority here. And that's the trouble with that, is that a lot of decisions aren't necessarily true or false statements. A lot of, conditions aren't necessarily true or false statements, and a lot of the time we want to do things where there is some notion of priority. So in traditional behavior trees, we would have a thing called a priority selector, which is one of these root nodes here that would actually select which of our children to run based on some notional priority value. But that's a problem because the Unreal Engine doesn't actually have that functionality inside it. So the one thing we could do is we could expand the Unreal Engine's AI to allow us to have some kind of priority selection, and I'm probably going to do that, but obviously I'll do that in C++ and not necessarily in the blueprints. So how can we do some utility thing in blueprints? And that's going to be the sort of the thrust of our work in the next few videos. So let's just talk about this idea of utility for a second. if you think about a behavior tree, right, what we're actually saying is that for any behavior tree node, we want to be able to choose from a set of options. Now, with within a behavior tree, if you're going to do it in a traditional sense, you'd have a thing called a priority selector that would actually ask each option, what is the sort of priority value for you to run? So, you know, if this guy was returning weight 5, that was returning weight 4, then weight 2, it would choose this one to execute. And similarly, if this guy returned weight 6, it would choose this one to execute. So this idea of priority selection is kind of, in normal behavior trees, is kind of common. But priority selection isn't the only way of doing these things. So there's this idea of utility as a concept. Is actually pretty simple, right? So what it does is it says we'll calculate some values, and I'll link some papers to Kevin Dill in the description of the video, but essentially he came up with this idea of a dual utility reasoner, and his implementation uses two values. One is the absolute sort of rank value, and the other one is a weight value. And he can think of them as absolute, as in sort of category type values, as absolute values, and then within the category as relative weights. So his example in the paper, that if you read it, is basically there's a sniper in a city and he's got a group of enemies that he can shoot at, and he wants to know which one to shoot. So there's an absolute value in terms of the sort of the absolute value of whether you should shoot an officer or a soldier, or a soldier. Obviously, the officer is in terms of an absolute value is better to shoot at because they have higher value as a target. But within those kind of categories, within those absolute values, there's also a relative value, right? So imagine that we're choosing which soldier to shoot. Imagine there's no officers left and we want to choose which soldier. Well, those are relative within groups, so based on some other value. So let's take this kind of setup as an example, right? So we've got to choose which of these guys we want to shoot. This is our choice, is like which enemy to shoot at. So we've got soldier 1, soldier 2 and soldier 3, and there's a couple of attributes. I mean, there might be a whole bunch of different attributes that come into this weighting, but let's just use these two right now. So they've got the military rank of private in soldier 1's case, and he's 100 meters away. We've got the military rank of officer, and he's 200 meters away, and we've got the military rank of private, and he's 300 meters away. So we might take the initial soldier and we would calculate a rank value for absolute rank value of 10. This is not military rank, by the way. This is just the thing that Kevin calls the absolute value. So an absolute value of 10, meaning that we've kind of ascribed soldier the rank of private to mean the value of 10. And then it's got the relative weighting of the weight of choosing this guy as 9, and we've used a distance kind of function to calculate this weighting value. So what we generally do in utility systems is that we have some kind of response curve, and if you look at the sort of curved blue line here, we might have a response curve that says if the guy's close, i.e. his distance is low, then maybe our utility value score is 1, right? So we'll turn a maximum utility. And as his distance gets further away, we kind of peter out, we sort of curve off, and essentially he kind of loses his utility as he gets further away. And this, obviously the curves that we can use might be completely different. There might be sort of different types of response curve, and we might just have like a curve that's actually ends up at this straight line. So basically there's lots of response, and then all of a sudden we allow some sort of fairly linear tail off. So we're actually going to have a look at using curves in our decision-making architecture in blueprints. There is actually a thing called a float curve that we can use, so we'll use that as part of our function. So going back to our example, the priority selector is essentially just choosing which one based on their rank value and their weight. So we've decided that the officer has rank 11, so that means that his military rank denotes that our category value is 11, and his distance gives us a function that returns the value of 0.8. So we then do it for the soldier 3, and his weight is 0.5 because he's obviously further away. So normally our decision making would choose rank as the first part, so our decision making would use the category of target as the main part of this value, and we would use the highest weight, or we'd use you remember how we did that sort of weighted random thing? So what Kevin says is that if you've got like a number of possible targets, what you should do is you should eliminate any with weight 0, and then you should do maybe cut off the bottom sort of 20% of those values as not being suitable, and then you should do a weighted random selection for anything that's left. So that's only if we've got things within the rank that returns the maximum rank. So in this case we'd always return the officer, right, because he's just got the maximum rank. But if you had this officer as a soldier, just a normal private, then we would be looking at the actual weight value for each of these as our deciding factor. So essentially we'd shoot the nearest guy because that was the weighting value that we returned from that utility. So Kevin talks about these deciding factors as considerations, and that's not a bad term for it. So what we would say is that all factors that affect an option, so all factors that affect sort of which option we choose, are based around these considerations, and these considerations can be kind of a modular system, and we'll look at how we might modularize that over the next few videos. But the idea is that we normalize each consideration to 0 to 1 range and then multiply them together. So essentially we allow any of these considerations to return a 0. So each consideration can essentially return a sort of false value in our true or false kind of version of the behavior tree. So essentially we can allow each consideration to disable that option as being a valid option by just returning a 0 in its value. So which means that all of the considerations potentially can affect the outcome of the decision. And we can think of considerations as things like how far is the target, I don't know, whether we've got a clear line of sight to them, whether they're looking in our direction. So there's a whole bunch of things that you might use as considerations in a target selection scenario. So the idea is that we create a data structure that essentially allows us to capture all of these considerations and then essentially get a normalized weight value for each one for each option. And eventually we get a 0 to 1 range floating point value for each option that we then use to then sort of say that that's the current score, and we take any ones that are 0 out, and then we randomize the things that are left so that we choose one of them, and maybe we actually sort of filter out some of the bottom weighted ones. If we've got lots of options, we might filter out the bottom weighted ones so that we know that we've kind of gotten rid of some of the worst options, and we're actually choosing from the available ones that are left. So that's the utility concept. It's actually pretty simple when you think about it. So what we're actually saying here is that the utility value, instead of being binary or true or false, is actually kind of a floating point range, and that we're actually kind of not choosing always the maximum, but we're choosing one that's in the higher end of that range of activation, so that we always get what we would consider as a reasonably good decision. And that means that we can have some randomness in our decisions, but we still have the bias towards a good one, rather than selecting poor ones because they're part of our randomization. So what we're saying is cull out anything that isn't possible. So cull out anything that our considerations have deemed impossible, and cull out any decisions that are poor, and then for all of the decisions that are left, we can just choose one at random based on the weighted random selection that we've done before. So that's what we're going to implement in our blueprints, using that weighted random selection function, or rather we're going to code a weighted random selection function in our blueprint code. The problem is that we can't actually apply that inside our behavior tree because the behavior tree just isn't set up for it. So what we'll have to do is actually do that as blueprint code inside our controller, which is not ideal, and ideally I'd like to see that the AI behavior tree actually have this kind of functionality built in. So I'm probably going to be adding that as C++ code, and hopefully Epic will accept that as a pull request sometime when I've actually done it over Christmas probably. Okay, so let's get on with some code. So the first thing we want to do is set up a couple of, well, I say a couple, set up two data structures. One is a blueprint type structure. So if you go to blueprints and then structure and create a new one of those, and I've called mine threat struct. And then the other one is if you go to I think it's miscellaneous and then curve, and I've called mine threat distance curve. So we'll look at those as we use them. So the threat structure itself, oops, wrong screen, is the thing that's going to hold the variables that I use for each actor to sort of to store its data from the perception system. So this is essentially, some of it I'm not using yet, we'll use it later on, but right now it's a way of capturing some data about the that particular pawn that we've seen. So if we look at the code for this guy, the controller, what we've probably already got is this. Let's just make that a little bit bigger. When you see a pawn, you check it's got a tag. Oh, here's another thing that I've done, is that I've added a function actor has tag. Takes the tags array. We had this code before. Essentially I've just moved it into a little function. So if you want to go to just expand that again, if you click on function, you can set up your function with inputs and outputs there. So I just wanted to say, if an actor, an input actor has one of the tags in the tag array, then outputable with true or false. It's just an easier way of having these nodes in the tree, and I'm trying to clean up things a little bit as I'm going. So essentially the logic is, so far if I see a pawn and it's got the tag that's associated with enemies, then I know it's an enemy, so store it in the blackboard key. So what we want is, we want first off, so I've shoved the enemy tags under an AI name. So what we want is a new variable. Let's go to variable, and it's of type, because we used that threat struct before, it's of type threat struct, and it's an array, and let's call that threats. So this is the thing that's going to hold our array of threats as we see them. So what we actually want to do, if you think about it, is that we basically say, if the actor has a tag and we basically can tell whether it's an enemy or not, then instead of doing this part of the code, what we actually want to do is we want to add that actor into a list of threats, or an array of threats. So let's just break that one out, and obviously we'll use this later on, so we'll probably just want to move it over there somewhere. Now then, what do we want to do when we're actually kind of adding the actor to the threats? So let's just think about the function that we need, right? So we're going to have some function that takes the incoming actor as a pawn and adds it to this threats array, but we want to only do that if we haven't got it already in the array. So there's a couple of things we need to do first, and that is to make sure that we haven't already got the actor in that threats array, right? So what I would suggest we do is that instead of just doing this, what we should probably do when we sense a pawn. All right, now let's do it in the inside a function, right? So let's create a new function, call it add actor to threats, and the type of variables it takes is an actor, so we want object actor, and we call that, let's just expand that again, input actor. So what we're essentially going to do is we're going to input an actor in. We probably want to do a few things, right? So I like to split this up with a sequence node. So the first thing we're going to do is we're going to check and make sure that this actor isn't already in the array. So the first thing we probably want to do is just make note of that. Let's take off that. So has, or rather is, actor in array. So first off, we want to, this is a local variable, and by local variable I mean that it's only available inside this blueprint for this particular function, so it won't affect anything outside of it unless we pass it in as a parameter, or obviously pass it out as a parameter. So we start off by, we'll do a sequence of two things. We'll set the variable to say the actors in the array to false, and then we'll do a loop over the actors. So what we want to do is a for each loop, and we probably want to be able to break it, so let's do that. We take the threats array as input. So what do we want to do? We want to first of all break the threat structure up. I want to say if the actor from this threat structure at the array element is the same as the input actor, so this guy here. So let's say equals, so if this guy equals that guy, so let's just move that down. So basically, if the actor that we're currently looking at is already one of these elements in the array, then what we want to do is we want to do an if, so for the loop body, if this condition is true, then we set the value of this guy to true. And then we break. So if it's false, we're just going to keep going through the array. So what that means is that, let's just save and compile it. What that means is that we've added a check if actor is already in the threats array. So, step one, check if he's already in the array, right? And we've set a Boolean flag to true if he is. So the next one is, let's do an if. So if actor is in an array is true, then what we want to do is, so there's part of it that says if it's true that the actor was already in the array, then we just need to update that actor. Now then, one thing we probably want to do is we want to store the index for when we saw this guy, right? So let's just add that now. Variable of type integer. We'll call it last seen index. So last seen index gets set over here. Let's just zoom in on that so you can see it. So, and the index is the index coming from the for loop. Let's just make that a little bit easier to see. There we go. Okay, so what we're doing is, if we start off by saying the actor is not in the array, we do a loop over all of the actors in the array. We say if our actors, if our structure's actor value is the same as the input actor value, then we know we found them, so we set that there is an actor in the array and we store where we saw them in the arrays in terms of index, and we break. So essentially this will never be set if we never see any of that particular actor in the array. So what we can say is that if we call get on this array and we pass it the last seen index, if this is true, then what we can do is we can break that threat structure up again. Let's just show all of the values in it, and there's a thing called set members, so we can set members in threat struct. So what we're trying to do is we're trying to give ourselves somewhere so that we can update some values. So basically get at that index that we found the structure for our current threat, and what we're going to do is we're going to essentially copy all of the values across, so actor to actor, etc, etc. But we want to damage receive, distance, rank, but what we want to do is we want to update the last seen, really, or rather we want to set the last seen to 0, because the last seen is basically like a counter. We can set the weight if we want to, but it doesn't really matter. But the last seen is essentially a count up value that says how long has it been since I last saw them. So when we see this actor, right, so the one that we're checking, we're saying yes, we've seen him in the array, so we've set a Boolean flag there. So we're saying if that Boolean flag was true, then we're resetting the last seen value in this particular value in the array. So what this should do is that we'll, in another loop, we'll count this value up. We'll basically increment this value every update, and if it gets over a certain value, then we'll be able to prune it out of the array. So like essentially time out actors as we've not seen them for a while, that kind of thing. So that's if we have seen them, right? So let's just put a comment there. Actor is already in threat array, so just update time since we last saw them. Now here's the thing, right? If we haven't seen them, well, we're just going to add them to the array, right? So all we need to do is we need to just do let's just call get on that. We're going to add a value to the array, and we're going to make threat struct, because this is a new one. We don't necessarily have to put any values in there particularly apart from the actor, because we're going to calculate these values as we update anyway. So essentially the last seen is a good value, and what we might want to do is just print a string after that. And say something like new threat added to threat array. And again, if this is false, then we're going to call the add. So actor was not in threat array, so add it. Okay, so that add actor to threat functions should be working. So we go back to our event graph, and what we're doing is we're essentially going to just call that function, right? So add actor to threats, and that is the input pawn that we're going to add, and it's the target on self, just because it's our object that's going to add it. So that's taking care of adding any new pawn that we've seen to the threats array, and obviously the next part we need to do is handle what happens. Let's just move that guy over there. Next thing we need to do is we need to handle like actually updating the threat values, and then we need to from there, once we've updated the threat values, we need to do things like actually select which threat to use, and then maybe a bit of cleanup, like forgetting which threats have expired, those kind of things. So the next part is that we want to add a tick event. Tick. Okay, so what do we need for the tick event to work? Well, there's a few things we need in terms of variables. One is that we want a float point value for let's call that elapsed time. We want another float point value, which is the threat eval frequency. I'll explain these in a second. And yeah, that should be all right. So you notice that delta seconds is passed into this thing. So what we have is there's this elapsed time value, and what we probably want to do is we want to increment that value with the delta time. So first thing we're going to call is set the elapsed time to be the current elapsed time plus the delta time. So the time since this tech was last called. We then want to say if if our elapsed time is greater, I suppose greater than or equal to is probably better. Let's just move those down a little bit. If our current elapsed time is greater than the threat evaluation frequency, so this is the thing that's going to control how often we update our threat values. So let's give that, let's just compile it, so we've added it, give it a value of, say, I guess 1 second. Now let's call it 5 seconds. So that just means that we're counting up a value here, and if the value reaches greater than or equal to our refresh rate, then we need to call another function, which means that we probably should have to write the function. What we can do is let's call set, actually no, let's just do it. We need to reset the elapsed time. So we're not going to do anything if we haven't elapsed. Otherwise we have reached the duration, so we just reset the elapsed timer. What we could do is subtract the threat evaluation frequency from it if we're going to be a bit more accurate, but for now it doesn't really matter. So that's our that calls for our next function, and that next one's going to be a bit big, so I think what we'll do is we'll just end this first video here. Let's just add a comment on this. If enough time has elapsed, if it has, evaluate threats, find greatest threat. Yeah. Now the one thing I would say about blueprints, by the way, is that you don't really want to be doing anything complicated in your ticks. And we're actually going to do a reasonably complex function at the end of this set of nodes, so it's a bit of a trade-off. That's where your performance will start to degrade if you've got too much stuff in your ticks. But this, the fact that we're only doing this once every sort of 5 seconds because we've got this elapsed time value, this will stop us doing too much work. Essentially this whole kind of set of nodes gives us a thing that only happens every now and then. What we could do is, like on begin play, we could set a timer and do this evaluation thing. It's kind of up to you really. It might actually be cleaner to do a timer based thing, but I like doing my own timings, I guess. So come back in the next video and we'll finish off a couple more of these functions and tie it all together, and then we'll see how it works. Okay, and see you next time.